Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. This video is all about the subject matter related to sizing of heat exchangers, heat exchanger design considerations. This course will be presented in two-part series. Part 1, selecting the right side for fluids and right geometry. Part 2, TEMA type heat exchanger classification and case study. In this course, you will understand how the geometry influences the heat exchanger sizing, the geometrical variables available as alternative to the process engineer or designer, TEMA type classifications of heat exchangers, importance of selecting the right heat exchanger, a case study. Heat exchanger design considerations. Thermal design of shell and tube heat exchangers is an iterative process which is usually carried out using process simulation software. Process modeling programs such as HTRI or HTFS are widely used. However, it is important for the process engineer to understand the logics behind the computations. The starting point of process design of heat exchanger is the design basis. What is design basis? Design basis lays out specifications of operating conditions and the environment in which the heat exchanger is going to operate. The environment means the operating environment such as corrosive and erosive nature of the fluids handled. The typical specification or data sheet for designing heat exchanger is presented here. It contains the fluids handled, the heat duty of the heat exchanger, the flow rates, the inlet outlet temperatures of the cold and hot streams, corrosive and erosive nature of the fluids, etc. This is a user specified data. The next part is thermodynamic properties of the cold and hot fluid streams. These are also included but generated by simulation. The user also specifies the maximum allowable pressure drop for the tube side and shell side of the heat exchanger. This is important because there are several equipments in the process plant, and every equipment experiences a pressure drop, and these pressure drop constitute the energy level of the particular unit. So the user does not want the pressure drop of the exchanger to exceed certain limit in order to limit his energy consumption. So this is an important part of the specification. Heat exchanger sizing means computation of area of the heat exchanger. To calculate the area, the heat transfer coefficients have to be calculated. without exceeding the pressure drop specified in the design. As explained a little while ago, the heat transfer sizing is an iterative process, whether it is manually done or by computer program. The cyclical iterative process is explained here. Assume overall heat transfer coefficient U. Then from the process data, area A is calculated. Then select a geometry, calculate the tube side heat transfer coefficient and the shell side heat transfer coefficient. Then calculate the tube side pressure drop and shell side pressure drop. If the tube side pressure drop meets the design spec, then tube side heat transfer coefficient is okay. If the shell side pressure drop meets the design spec of the shell side, then the shell side heat transfer coefficient is okay. Then you proceed and calculate overall heat transfer coefficient U actual. Then compare U actual with the U assumed. If they are the same, then your design is okay. If it is more or less by huge margin, then reassume U and start the process all over again. Here the cyclic iterative process for tube side design is highlighted separately. Determination of tube side heat transfer coefficient for the calculated A. Decide on the geometry, proceed to calculate tube side heat transfer coefficient, calculate the tube side pressure drop. If the tube side pressure drop meets the design spec on the tube side, the geometry is okay. You can stop the calculation further. If the pressure drop exceeds or too much less, revisit the geometry, change the geometrical data and restart the calculation again. Here the cyclic iterative process for shell side design is highlighted separately. Determination of the shell side heat transfer coefficient from the calculated A. Select the geometry, proceed to calculate shell side heat transfer coefficient HO, calculate the shell side pressure drop. If the shell side pressure drop meets the shell side design spec pressure drop, the HO and geometries are okay. If the pressure drop is more or less by huge margin, go back to geometry, change the geometric data and recalculate the pressure drop and heat transfer coefficient again. Two important things to note in the sizing are overall heat transfer coefficient U and the geometry. You should have the knowledge of the value of U. That is a starting point. The values of overall heat transfer coefficient is available in the literature for several fluid combinations. The second point is the geometry. This is the critical decision-making stage for the design. Several initial design decisions need to be made with respect to the fluid streams, heat exchange geometry and configurations. These decisions are altered during each iteration in order to maximize the overall heat transfer coefficient without exceeding the allowable pressure drop. Do you know what are the geometric data concerning the design? You can find it here. The type of heat exchanger, as per TEMA classification, you have to select. Then the material, whether carbon steel or any other special material required depending on the application. Length of the tube alignment, whether it is square pitch or triangular pitch, tube spacing, tube dimensions, number of baffle plates, spacing of the baffle plates, and free cross section in the shield area, which is a baffle cut. Selecting the right side for the hot and cold fluids. Selecting the side for routing the shell side and tube side fluid has a significant impact on the design of shell and tube heat exchangers. Shown here is a shell and tube heat exchanger. Look out for the shell side and tube side in the exchanger. Which fluid stream you will select for the shell side? Which fluid stream you will select for the tube side? High pressure. High pressure is one of the factors in making the choice. Position high pressure fluid on the tube side. This normally minimizes the exchanger cost. High pressure needs higher thickness of the wall. The smaller tube diameter has a higher pressure rating for the same metal thickness compared to the larger diameter shell. The next important parameter in selecting the right side is fouling. Processed fluids or utilities like cooling water have a tendency to foul the heat exchanger. Fouling offers heat transfer, and after a certain period of time, the heat exchangers need to be cleaned to restore the original clean surface condition as well as heat transfer capacity. Hence, the allocation of fluid to the tube or shell side should be such that it facilitates cleaning of the exchanger effectively. A fluid with a fouling tendency should be generally routed to the tube side, irrespective of whether it is a fixed tube sheet or removable tube bundle. Shown in the figure is a shell and tube heat exchanger with various stream nozzles shown on the tube side and shell side. The heat exchanger has two tube passes and one shell pass. The partition plate on the front channel makes it possible to achieve two passes on the tube side. Fouling liquid is routed to flow on the tube side. As long as the tube is clean, the heat transfer is fine. As the tubes gets fouled, the heat transfer gets affected and the process stream temperature starts to increase at the heat exchanger outlet. If the heat exchanger fouling progresses, at a certain point of time, you have to stop the heat exchanger and clean the tube. The sketch shows how the cleaning of fouled tube is possible and can be done as shown in this figure. Instead, assume that the fouling fluid is allocated to the shell side. Now the fouling occurs on the outside surface of the tube. How will you clean the surface? You cannot access outside tube surface from the shell. Only way is inlet and outlet nozzles, which makes the cleaning impossible. Shell side cannot be cleaned without removing the tube bundle. Even in the case of removable tube bundle, the accessibility at 360 degrees is not possible. When both fluids have a tendency to foul, and the fluid having more severe fouling characteristic should be put on the tube side. Cleaning straight tubes normally is easier than cleaning the shell. A tube layout with a relatively large tube pitch is often chosen to facilitate cleaning of tubes on the shell side. In spite of these arrangements, cleaning of tube on the shell side is never easy. Presence of baffles and the tie rods create additional difficulties. The exchanger configuration has a considerable impact on the selection. With thick tube sheet, there is no alternative except to put the clean fluid on the shell side. In cases where it is possible to remove the scale or deposit by chemical cleaning, one may consider putting the fouling fluid on the shell side as a last option. U-tubes are more difficult to clean than straight tubes. In this case, it is better to select the shell side for the fouling fluid by taking special design precautions to minimize fouling, such as installation of helicate tubes, etc. C. Expensive materials for corrosive services. Corrosion is a chemical reaction between the process fluid and the metal parts of the heat exchanger. More severe is the corrosive nature, the more the corrosion rate, and consequently more will be the damage to the metal parts of the heat exchanger, like tubes, tube sheet, shell and other parts in contact. So keep the corrosive fluid on the tube side. This will keep the shell from contacting the corrosive fluid. Only the tubes, tube sheets, heads and channels will be in contact with the corrosive fluids and need expensive corrosion resistant materials. If you put the corrosive fluid on the shell side, the entire heat exchanger has to be made of expensive corrosion resistant alloys. D. Low pressure drop. One of the most important specification parameters for designing heat exchangers is the pressure drop. The heat exchanger geometry and configuration is selected such that the tube side pressure drop and shell side pressure drop do not exceed specification limit. The fluid requiring lower pressure drop, such as the process fluid, should go to the shell side. Several design parameters of the heat exchanger, such as a baffle cut, type of baffle, baffle spacing, will influence the shell side pressure drop. You will understand these geometry data in the discussion that follows. This figure illustrates what is a pressure drop and how it is measured. The fluid at the inlet is at a higher pressure than the fluid that is leaving the heat exchanger. With reference to the figure, P1 is the pressure of the fluid at the tube side inlet and P2 is the pressure at the outlet on the tube side. The difference is the tube side pressure drop, that is P1 minus P2. Likewise, P3 is the pressure at the shell side inlet and P4 is the pressure of the fluid at the shell side outlet. So the difference between P3 and P4 is a pressure drop on the shell side. Carefully selected combination of baffle cut spacing and type of baffle can make the design to meet nearly any pressure drop requirement. Service under vacuum almost always are on the shell side because of the pressure drop sensitivity of the column. The next consideration is the vapor services. Vapors are generally put on the shell side. Owing to lower density, the volume handled is usually large for the vapors and the heat transfer coefficient is lower than a liquid. This figure illustrates visually the large space available on the shell side and hence vapors with large volume should be allocated to the shell side. This will help to achieve lower pressure drop for a given volume and also provides higher heat transfer coefficient. The next design consideration is condensing services. A condensing fluid is most often put on the shell side. In most of the condensing applications, cooling water is a cold fluid, and from the fouling point of view, you should go to the tube side. If the vapor is a single component or relatively pure mixture, the entire overhead vapor condenses and only the liquid or condensate leave the shell from the bottom. If the mixture is a multi-component or has a large non-condensable components, the shell side design should take care of the vapor liquid separation and draining requirement. Next design consideration is viscous services. All of you are aware, highly viscous fluid experiences larger pressure drop as the resistance flow is larger. From pressure drop consideration, the high viscous fluid is usually put on the shell side. Otherwise, excessive pressure drop across the tubes will make it difficult to meet the process requirement. Care must be exercised, however, to ensure that the high pressure drop on the shell side does not lead to liquid bypass around the baffles, which will reduce the heat transfer. Having understood how to allocate the right fluid to the tube side and shell side of the heat exchanger, we will move on to understand how to select the right geometrical parameters in the design of heat exchangers. As explained in the beginning, selecting the right geometry is crucial design consideration both for the overall heat transfer coefficient and shell side and tube side pressure drop estimation. First, selection of tube layout. Most commonly used layout for heat exchanger design are shown in this figure. Square pitch and triangular pitch. Though there are other layouts such as rotated square pitch are also available. For which service and under which condition each of these two layouts are used, we will move on to find out. Triangular pitch is better for heat transfer and surface area per unit length. Triangular pattern provides a more compact arrangement and robust tube sheet construction as well as smaller shell for a specified cell side flow rate. In the figure shown, the tube side nozzles have been cut and removed to show you the tube layout for the heat exchanger. You can see the tube layout for this heat exchanger is triangular. Square pattern is required for mechanical cleaning of tubes on the cell side. Square pattern has a lower shell size pressure drop. For identical pitch and flow rates, the triangular pattern has highest heat transfer coefficient and the highest pressure drop. Square pitch layout will have the lowest heat transfer coefficient and the lowest pressure drop. For certain services such as liquid heat exchanger, high temperature gas services, fouling services, square pitch layout is preferred. Hence, this decision must be taken with the due knowledge and understanding of the process. The tube pitch is usually chosen so as to have a pitch ratio of 1.25 to 1.5 times the tube diameter. The next geometry related design consideration is selection of tube size. The heat transfer area on the tube side is determined from the expression number of tubes times the heat transfer area of one tube. Heat transfer area of one tube is obtained from the expression given here, which is a function of outside tube diameter and length. The outside diameter of the tube is a design parameter to decide while sizing the heat exchanger. Typically, 3/4 inch tube is selected. For certain special applications, 1 inch size is selected where the fouling is expected to be high. Large diameter tubes are easy to clean. For mechanical cleaning, Smallest possible size is 3/4 inch. For chemical cleaning, smaller size can be used. Tube size is designated as 3/4 inch BWC. BWG stands for Birmingham wire gauge. Birmingham wire gauge defines the wall thickness. For greater heat transfer area, smallest diameter may be used with the normal minimum of 3/4 inch OD tube due to cleaning consideration and vibration. Another geometry parameter that needs to be considered during design is tube length. In the figure illustrated, the shell has been cut to expose the tube side so that you can visually see the tube length. The tube length is measured from tube sheet to tube sheet. In a U-tube heat exchanger, it is measured from tube sheet to the point where the U-bend begins. The standard tube length for carbon steel tubes are 4.871 meters, 6.096 meters, 12.192 meters. The length of the tube is decided based on the space available to install the heat exchanger in the plant. While space availability is a concern, shorter tube length of 4.877 meters can be selected. Another important consideration in the heat exchanger design is baffles. What is the role of baffles in the shell and heat exchanger? The function of the baffles in a shell and heat exchanger is to direct the flow across the tube bundle as well as to support the tubes from sagging and possible vibration. Baffles increase the velocity and are treated as a design variable to increase velocity to obtain higher heat transfer coefficient. This figure illustrates what are baffles and how they are arranged in the heat exchanger. You can see how baffles support the tubes from sagging and preventing possible vibration due to the flow. The flow pattern due to the baffle arrangement is illustrated in this figure. The fluid, upon entering the shell through the inlet nozzle, move down and then up, then down in a sequence across the heat exchanger till it reaches the outlet nozzle. Note that the presence of baffles in the shell side of the heat exchanger increases the pressure drop on the shell side because of the restriction area. However, the advantage of the better mixing and turbulence more than offsets the pressure drop. One of the important geometrical parameter related to baffle is baffle spacing. What is baffle spacing? The distance between the baffles is called the baffle spacing. In general, baffles should not be placed closer than 20% of the inner shell diameter. In general, baffle spacing is determined from this formula B. The baffle spacing equals to 0.3 ds, where ds is a shell diameter. Baffle spacing is a variable in estimating the cross flow area on the shell side and shell side velocity of the fluid. Closed baffle spacing gives higher turbulence and hence greater heat transfer coefficient. Another design parameter related to baffle is a baffle cut. Baffle spacing and baffle cut decides the heat transfer coefficient and the delta P in the shell side. The most common types of baffles used in the shell and tube heat exchanger is a segmented fable, which is illustrated in the figure next. In cut segmental baffle, a segment called baffle cut is removed to form the baffle expressed as percentage of the baffle diameter. Baffle cuts from 15 to 40% are normally used. A baffle cut of 25% provides heat transfer with reasonable pressure drop. The percent cut for segment baffle refers the cutaway height from its diameter. Shown in this figure is a cut segmental baffle. The flow pattern is also shown across the baffle here. The cutaway portion, as shown, provides the area for the flow. This figure shows other baffle types. The first is the discount donut. The baffle construction has a donut and disc around which the shell side fluid flows. Orifice baffle is another type. These are used only for certain applications. When the shell side pressure drop is higher than the specified value, baffle spacing can be manipulated from 25 to 40% of the shell side diameter to adjust the velocity and consequently the pressure drop. But this will reduce the shell side heat transfer coefficient H2O. It should be taken care and recalculated. We have covered all the relevant fluid allocation and geometry related design consideration for the shell and heat exchanger. I am sure this video would have made you realize the importance of understanding the design considerations before you set out to begin the design. Subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation on part 1 of the two-part series of heat exchanger design considerations. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you have finished viewing this video. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing their knowledge base. Thank you for watching.